Well, good morning, good afternoon, and even good evening to our friends across the Atlantic. Welcome to Moberg Analytics Case Studies in Neurocritical Care AI webinar. We're very happy to have you here today. Um, as you know, as you're all well aware, treating and understanding brain injury is a gigantic mission, and our goal with these webinars is to help you in that mission in some small way. We do that through these webinars. We provide cases and examples. We have data and tools to help you with those problems. We also have starter grants of cloud and consulting if you have a project you're trying to get off the ground and bootstrap. Please provide us feedback on the webinars. You can do that through that QR code, or sending me an email directly at craig@moberganalytics.com, or the webinar feedback link there on that bit.ly. So we'd love your feedback on improvements. If you know of people who are doing cool and interesting things that would make a good topic, please reach out to us. Or most importantly, if you've got your own work, we'd love to hear from you. So volunteer to speak. This doesn't work without all of the brilliant people coming forward and helping us with these webinars. So we'd love to hear what you're doing. We are getting quite a library. I'm almost gonna have to switch to a two-page, or really get the font down, or maybe I just won't be able to put them all in here. But we've got a huge library of replays that are available on our YouTube channel or via that link off of our website, the webinar videos link off of our main website. So feel free to go back and check those out as time permits. If you have questions, please use the Zoom webinar Q&A feature, and everyone's pretty familiar with that by now, I assume. So let's kick it off. So today we welcome Jennifer Briggs from University of Colorado Anschutz Medical Campus, where she is nearing the finish line of her PhD in bioengineering. So she'll be graduating this August. So nearly congratulations. I'm sure that's just a gigantic achievement. So pre-congratulations. She did her lower division work at Pepperdine, where she double majored in physics and sports medicine, and with a minor in applied mathematics. And so she began her math journey out in space. She studied the magnetosphere and the Aurora Borealis and did really cool things like that. Over the course of her work since, she's brought that experience to medicine, and specifically in cerebral vascular physiology, and more specifically in neurocritical care. So she's taken all of that cool stuff she learned out in space and brought it very close and very near to our hearts. Today, she's going to present some very interesting work she just published, and it centers around using uncertainty quantifications to identify sensitivity in PRX, which allows for development of possibly a more personalized PRX. So it's really cool and interesting work. We were all fascinated. She went over it with Dick, Ethan, and I a few weeks back, and we said, well, you must come and show this to more people. And fun fact, she and I learned through the course of our interactions that we used to live in a tiny little town on the Colorado Front Range near Colorado Springs, and we even used to run through each other's neighborhoods unbeknownst to one another. So that was a fun fact, because we still couldn't believe that there was somebody who actually knew this little town. So anyway, with that, Jennifer, I will stop sharing and turn it over to the interesting part of this presentation. And you're still on mute.
All
There you
right.
go.
Can you hear me? Can you
Yes.
see my screen?
Yes,
Um,
perfect.
well, thanks for having me. And yes, Craig, the discovery that we were both from a tiny mountain town that no one has ever heard of was quite a joy and nice to be seen. So thank you each for having me. This is such a wonderful community, and I'm excited for the opportunity to present. And as you heard from my background, I'm not a neurologist, although I work with some fantastic ones. So hopefully through this presentation, we can have a very lively discussion over kind of the combination of applying these mathematical tools to something that really matters, which is neurocritical care. So let's dive in. I don't have any disclosures. My only disclosure, I guess, is that given that you're here, I'm just going to go ahead and assume that you think neurocritical care is important. So I'm not going to spend much time motivating the importance of studying the cerebrovasculature. And so let's just start assuming that we have a patient who's come into neurocritical care, the ICU, and a primary goal with neurologically injured patients or brain injured patients is to ensure that their cerebral blood flow is optimal to prevent secondary injury. The cerebral vasculature is highly complex, as you probably know, and you can see in this little cartoon image on the right. But in general, if you take a bunch of averages over time and cerebral blood flow is roughly driven by a perfusion pressure. This is called the cerebral perfusion pressure, and it's created by the gradient between arterial blood pressure and intracranial pressure. But there's a reason that our blood flow isn't just perfectly proportional to our arterial blood pressure, and that's because blood flow is also driven by some other quantity that is typically referred to as something like cerebral vascular resistance. And from a physics perspective, the resistance to flow can be thought of as the combination of blood viscosity, the bifurcations in your vasculature, and most notably the radius of the vasculature. And so, as you probably know, the vasculature has this incredible ability to change the radius in response to lots of different signals in order to make sure that your blood flow is always optimal in healthy conditions. Our ability to measure and understand how well the vasculature is changing radius at a given time is quite limited. And so one way that we can go about doing this, which I'm sure you all are familiar with, is this concept of cerebral autoregulation. Now, in cerebral autoregulation is what we call an empirically defined phenomena, which means it's not defined based on the cellular mechanisms that are underlying it, but rather it's defined based on what we've observed. And so for many, many years, we've known that if you change the blood pressure of a patient over large gradients, in healthy patients, there's typically a range for which the vasculature radius is able to change to compensate for changes in blood pressure such that blood flow is not impacted. These are called the lower and upper limits of autoregulation, and they're very important to make sure that we get proper blood flow to the brain. Now, neurological injury is often thought to impair autoregulation, and typically that impairment is defined as a decrease in the range of these upper and lower limits, such that the range for which blood flow is not proportional to pressure is limited, and outside of these ranges, your blood flow is completely proportional to your pressure. And so in neurocritical care, it becomes really important to make sure that these pressures are optimized in order to make sure blood flow is adequate. Now, I'm assuming a lot of you have done some incredible work looking at cerebral autoregulated guided care in neurocritical care patients. And this is just a very small subset of some of that beautiful work, showing that there might be a lot of potential in improving outcomes by guiding care based on the function of a patient's cerebral autoregulation. But as I alluded to before, autoregulation is a very challenging thing to measure. It's challenging to measure even in perfectly controlled experimental settings or even in animal settings, but this challenge is increased exponentially in unstable neurocritical care patients. And so if we go back to this little diagram, as I mentioned, autoregulation is empirically defined based on effectively how related cerebral blood flow is to blood pressure. So the kind of clear next step in potentially quantifying cerebral autoregulation is just saying, well, how correlated is blood flow to blood pressure? There's two somewhat complex situations in which we have to change this a little bit. So the first is that work a while ago showed that the cerebral autoregulation seems to only operate on slow frequencies. This was an experimental work that found that autoregulation doesn't seem to impact frequencies of heart rate and breathing, but rather these slower frequencies. And so, okay, that's possible. Maybe we can somehow pass some kind of signal processing over CPP and CBF so we get these slow frequencies. But the other challenge is that measurements of cerebral blood flow in the ICU or neurocritical care are exceptionally limited. Instead, what we usually have are measurements of ICP and measurements of ABP. And so the work of the Cambridge group primarily came up with this lovely idea that in some ranges, changes in intracranial volume can be directly proportional to changes in intracranial pressure. You can assume that you can kind of get a proxy for blood flow if you measure pressures. And so that is what is called the pressure reactivity index, which I'm sure many of you are familiar with, which takes this assumption that if we're in the regime where pressure is proportional to volume, you might be able to correlate arterial blood pressure and intracranial pressure and get some idea of how functional cerebral autoregulation is. So the pressure reactivity index, which was developed in the late 90s, takes these messy, noisy signals of arterial blood pressure and intracranial pressure and passes a non-overlapping moving average window to remove some of these faster frequencies, and then correlates between some amount of average samples between ICP and ABP, and that correlation coefficient is what's called the pressure reactivity index. And it's thought that if the pressure reactivity index is high, near 1, that autoregulation is extremely impaired. And the lower the correlation, the pressure reactivity index, the more functional cerebral autoregulation is thought to be. Now, when we came into reading about this, the first kind of question we had is, so the size of this averaging window and these correlation windows are what are known as hyperparameters in an algorithm. What that means is that size has to be set a priori or before the calculation occurs in order to be able to calculate PRX. And when scrolling through the literature, we noticed that the hyperparameters used are quite variable. My understanding, if I recall, the first kind of set of PRX papers used this 6-second averaging window with larger numbers of samples for correlation. And now a lot of literature has moved towards this 10-second averaging window and the 30-sample correlation. And so the question that we had originally was, what are the effects of the hyperparameters on PRX? Do they matter? If so, what hyperparameters should we use? And if they matter, then are there ways in order to reduce external error in order to improve PRX robustness? Now, the deepest challenge underlying PRX is that the reason this algorithm was created is because we don't know how to measure CA. So if we don't know how to measure CA and we don't have a gold standard, how do we compare or quantify errors? So we did this in a few different ways. We did this through both kind of an uncertainty quantification approach and a simulated data approach. And I'll mostly be showing you the uncertainty quantification today. So what we did is we collected 21 patient data sets from the TRACK-TBI data set. And we just calculated PRX for an extremely wide range of hyperparameters, that range encompassing all of those common hyperparameters I showed in the last table. And what you see here is the empirical error, which was the median PRX calculated from a given hyperparameter minus the average PRX from many hyperparameters. So this goes back to this idea of we don't actually know the gold standard, so how do we calculate PRX error? What we assumed is that let's calculate PRX over many hyperparameters and take the average, and that'll be kind of our, not truth, but it'll help us understand, it'll help us have a comparison. And so what you see here are the 21 data sets calculated for each hyperparameter. And I want you to see two things. The first is that these 5 violin plots are different. And what that means is that empirical error, or the error in PRX, is dependent on the hyperparameter, which is important when we're looking at literature that uses different hyperparameters. But also what I want you to see is that the hyperparameter dependency is patient dependent. And what I mean by that is the following. So if you think back to probably high school math, you may have learned about this idea of precision and bias, where bias is how close, if you're shooting, arrows at a target, bias is how close to the center of the bullseye can I get? In this case, it would be how close does PRX get to the actual value of CA? Low bias is good. But precision is also a metric that gives us how clustered or close together are my targets or arrows in this case. So for example, up here on the top right, we're not close to the bullseye, but also high precision. All of our arrows are hitting the same area. And so what this means in the context of PRX is if we have a high bias but high precision estimator, then if we can calculate the bias in PRX, we can just adjust for it, and it's not a problem because we know that for all patients, we're kind of getting around the same bias. But what we see here, especially with these shorter averaging windows of 5 seconds and 6 seconds, is that each very different error, which means that we have very low precision, at least for these hyperparameters. And what that means is something about the patient is impacting how PRX is calculated and how the error, and what the error is. And I want to clarify, PRX is trying to identify differences in CA function. So you want a different PRX for each patient, but what we see here is not that the PRX is different, but that the error and sensitivity to hyperparameters is patient dependent. And so that's a problem, especially when we want to kind of extend the use of PRX into different populations. Here's just some other ways to look at this calculation. So here's an example patient for which we calculated PRX using these 5 hyperparameters. And this is the ideal circumstance. You see the different colors are PRX over time, and you see that in general, PRX is very similar for each hyperparameter. Now, as a lot of you probably know, clinical decision-making is not necessarily based on the value of PRX often, but it's based on the cerebral perfusion pressure value that is associated with when PRX is minimized. I will clarify that this is calculated in a nicer way than I show here. This is called cerebral perfusion, CPP-opt, and it's calculated using kind of a parabolic fit. But the idea is the same, that you want to identify the cerebral perfusion pressure associated with low PRX values. So this is an example of one patient in which PRX is minimized at the same value, and it looks about the same, and it's minimized at the same time for all hyperparameters. Now, here's a different patient for which there's a little bit more variance in the hyperparameters, but importantly, when PRX is minimized, it's minimized at the same time, which means it would correspond to the same minimal, the same cerebral perfusion pressure. But what you see is some hyperparameters calculate a very low PRX value, and some hyperparameters calculate a much higher PRX value. Now, this is also somewhat variable in the literature, but typically it's thought that PRX over 0.2 is predictive of poor outcomes, and PRX less than 0 is predictive of very functional outcomes. And so what you see here is that the best PRX we get is completely dependent on the hyperparameters, and potentially these hyperparameter sensitivity has impacts into the actual interpretation of how functional this patient's cerebral autoregulation is. Now, this is an example of maybe the worst case scenario in which each hyperparameter has about the same, a relatively similar PRX value that's minimized, but the time at which it's minimized is quite variable. And so we plotted here in the blue also the corresponding cerebral perfusion pressure binned by, I believe it was 5 minutes. And what you can see is that the corresponding cerebral perfusion pressure that corresponds to these negative minimum PRX values is quite wide, depending on which hyperparameter you use. It ranges from about 10 milligrams of mercury. Now, I'll again kind of mention that cerebral perfusion pressure, CPP opt, is not necessarily calculated this way, but the idea is still similar. So what this means is that the hyperparameter sensitivity is patient dependent and it could have a clinical impact. And then the last way we went about quantifying hyperparameter sensitivity, again, to try to kind of triangulate this fact that we don't know the true PRX value, is what you see here is an example contour plot of 5 different patients, which correspond to the previous slide, and their PRX values for many, many, many different hyperparameters. And you see with this patient, interestingly, with extremely impaired cerebral autoregulation, the hyperparameters don't matter very much. You see in black are the common averaging windows, and PRX value is pretty much the same no matter what you choose. But as you go down this graph, what we can see is the hyperparameter sensitivity starts becoming more extreme and more patient dependent. And for patient number 5, which is this patient that I mentioned before, depending on the hyperparameter you use, you can range from an estimated PRX value of -1 to +1, which is fairly extreme and a bit problematic when we're trying to use PRX to estimate CA function. Just some other ways to quantify this sensitivity. On the right in the purple, you see the range of PRX values. So this is just the range of the most common hyperparameters. And we can see that some patients, the sensitivity is almost nothing, where other patients you get about, excuse me, up to 0.3 difference, which again, if the critical threshold between functional and dysfunctional CA is 0.2, an error of 0.3 is quite substantial. And then we also just calculated if you just change the hyperparameter by 1 second averaging window or 1 correlation sample, how much does that change PRX? And again, you have some where it doesn't make a difference at all, and some where the change in PRX is over 200%. And so there is a hyperparameter sensitivity, and these PRX errors are patient dependent. But PRX has obviously been proven to do really impressive things, and I don't want to say that just because there's a sensitivity doesn't mean that the PRX is not a good metric. I think it's a fantastic metric. And so what we wanted to do is say, especially this PRX patient dependency, is there a way we can help reduce it? And so using simulated data, we started just looking at what are kind of some of the things that might be impacting CA. And with simulated data, we can actually define a true PRX because we defined the data. And what you see is that there's a very clear heart rate dependency between error and PRX. But this is simulated data, and there's a lot of problems with the simulated data. And so, excuse me, if we look at patient data, we also quantified the heart rate dependency. So here you see median PRX calculated with the most common hyperparameters, 10 seconds and 30 samples, and its dependency on heart rate. And interestingly, there's a very clear linear correlation between heart rate and median PRX. If we look at the range of common hyperparameters, which is what I talked about before, gives us an idea of hyperparameter sensitivity, you can see again that there's this kind of clear range between average heart rate and heart rate hyperparameter sensitivity. Just 2 other ways we can look at this. If we calculate PRX using the largest hyperparameter window, which is 10 seconds averaging and 40 sample correlation, there isn't a relationship between empirical error and heart rate. But if you look at one of the smaller ones, there is a trending relationship with a p-value of 0.8 0.08 between heart rate and empirical error. And so this gives us this idea that maybe there's a heart rate dependency underlying the errors in PRX. And this actually makes a lot of sense from a mathematical perspective for two reasons. The first is that computed averages are dependent on the number of samples present in that computed average. And if you think about an arterial blood pressure waveform, heart rate is the largest and the fastest frequency, and it's also the primary frequency that we're trying to average out in order to calculate CA. And so the heart rates present in the averaging window can be thought of as the samples. When heart rate changes, either within the patient or between patients, the number of heartbeats in the sample changes. And that will induce variability in the average. The other reason why heart rate likely has an impact on PRX error is because heart rate will impact whether the full pressure waveform is included in the average. And I think this is best explained by a picture. So I drew this somewhat terrible arterial blood pressure waveform plot, but let's just say we want to take an average. Ideally, you start at the beginning of a pressure waveform and you end at the end of a pressure waveform, right? So then you get the full pressure waveform and hopefully you get the same number. But given that PRX is a moving, non-overlapping average with a fixed time, almost certainly you will not get this consistency of the beginning and the end of pressure waveforms. More likely you'll get something in the middle. And so in this red plot, what we see is potentially beginning at the average halfway through the pressure waveform and ending maybe at the end. And so in this red average, what you get is you're capturing more of the smaller values of ABP. And so this is going to negatively bias that particular average. And so that's what I mean when I say that heart rate is going to impact how much of the pressure waveform is present in each averaging window. And so we wanted to identify a way to reduce some of this heart rate dependency without requiring significantly more computational impact or requiring the addition of different measurements. And so what we did is we said, what if we can write an algorithm that automatically identifies heartbeats? And so we wrote an algorithm that inverts the pressure waveform and uses the sliding averaging peak identification to identify these heartbeats. And then we said, well, if the problem is that we need the same number of heartbeats in each window, why don't we just average over a consistent number of heartbeats rather than seconds? So what we do is we reparameterize the averaging window from time to heartbeats. And so this is what that averaging will look like. And so you can see that it is somewhat consistent. And so if we look at what we're calling this personalized pressure reactivity index compared to the standard time domain-based pressure reactivity index, in this patient, what you see is that the blue, the personalized algorithm, might show a little bit less noise compared to the standard algorithm, and indeed quantified in all the patient data using common hyperparameters, you see that there's a decrease in noise. Additionally, you see that there's a statistically significant decrease in the sensitivity to hyperparameters in this personalized algorithm. And now, of course, we wanted to know if we're actually removing heart rate sensitivity. So is this algorithm even working? So on the left, again, you see this personalized pressure reactivity index. On the right, the standard reactivity index. And this is the range of common of PRX values across the common hyperparameters, which gives us an idea of sensitivity. And you see that in the personalized algorithm, there is no relationship between heart rate and sensitivity, where in the standard algorithm, as I showed before, there is a relationship. If we look at empirical error for the hyperparameters that did show a heart rate dependent sensitivity, you can see that that sensitivity is removed. And then interestingly, if you look at actual computed PRX, there is still a heart rate dependency, but slightly less statistically significant. And so that what that indicates to us is that while we're removing the heart rate dependent errors, there may still be a heart rate dependency in actual CA function. And this makes sense for a variety of physiologic reasons. We also just compared the raw median PRX values computed with personalized and the standard algorithm. And you see this trend where patients with what you would consider kind of absent cerebral autoregulation function, so PRX greater than 0.2, the personalized algorithm seems to estimate a higher PRX or a more absent CA, whereas patients with functional CA, the trend is the opposite. And so if this personalized algorithm is getting at a more accurate assessment of CA, what that means is that we can get a even more variability in CA function, which is quite interesting. But this personalized algorithm requires work. It requires heartbeat identification, and maybe you don't trust it. So we also just wanted to look at, are there hyperparameters that are more ideal than others in the standard algorithm? And so what we did is we took all of our PRX values in both simulated and patient data, and I'll walk through this kind of slowly. So on the x-axis is the correlation windows, on the y-axis is the averaging windows. On the top row, you see the standard deviation and error, which just gives us how sensitive, or the noise. And then down here, you see kind of the average error, either raw error in the simulated data or empirical error in the patient data. And what we did is we just highlighted the areas for which the standard deviation of error was minimized in both simulated and patient data, and the actual raw error was minimized in patient and simulated data. And we identified the hyperparameter values for which these minimal error areas overlapped. And the only hyperparameter value within kind of that list of common hyperparameters is this 10-second averaging and 40 sample correlation. And so we split this into two data sets just to make sure it's not necessarily the training of a machine learning algorithm, but we wanted to see if the errors were translatable. So here you see only that's what we're calling the developmental data set. In red is the PRX standard deviation of error calculated with the most common hyperparameter that we identified as optimal, and then the other colors are the other common hyperparameters. And you can see by visualization that the standard deviation of error is lower and less variable, which is good. And then if you quantify this, you also see a statistically significant decrease in the standard deviation of error for both the development and the patient data set. So I would recommend, given these findings, that we use an average of 10-second and 40 sample correlation. That being said, given that we have these ideal hyperparameters, what's the point of the personalized algorithm? I think one of the points, besides heart rate dependence and the fact that if heart rate dependence impacts the error depending on patient, that's a problem, is that if we use the standard algorithm, even with an ideal hyperparameter, we're still going to have challenges with hyperparameter sensitivity given the missingness of data. So if you've looked at a pressure waveform in neurocritical care, you probably know that if a patient coughs or moves or something happens to their monitor, the data are quite erroneous. And so oftentimes we have to remove them. And practically, the removal of data is equivalent to changing the hyperparameters. For example, if your hyperparameter is a 10-second averaging window, but 2 seconds of that data are missing, you now have an 8-second averaging window. And so the hyperparameter sensitivity is a potential problem, even if you're using one hyperparameter across all of your studies. So in conclusion, as Craig mentioned, this was just published in IEEE Transactions on Biomedical Engineering, but it's also posted on medRxiv if you want free access. What we did in this study is we took the existing PRX algorithm and we quantified hyperparameter sensitivity, intrapatient variability, sensitivity, error, and noise, and we saw that they were relatively high given the critical threshold for CA. We then identified ideal hyperparameters, and that obviously doesn't change hyperparameter sensitivity, but those ideal hyperparameters did decrease noise and did decrease the interpatient variability. And we also developed a new algorithm called the Personalized Pressure Reactivity Index, which our findings indicate may improve the PRX estimate. So that's kind of the main takeaway of this. I'm gonna spend just a few minutes chatting about some of our more recent work because it's something I'm really excited about. But it's not going to be, it'll probably take like 5 minutes and won't be very comprehensive. So while PRX is well known and obviously quite is becoming quite important in neurocritical care, the things that PRX can't do are forecast and estimate the actual function of mechanisms underlying CA. I mentioned that cerebral autoregulation is empirically defined, but we know that cerebral vascular regulation, or the just reactivity of the vasculature, is quite complex. And it's thought that there are at least 3 physiologic mechanisms underlying vascular regulation. These include the myogenic mechanism, which is that mechanism that's dependent on cerebrovascular tone and is likely mostly predominant in kind of the CA idea. There's also the metabolic mechanism, which changes the vascular radius due to changes in metabolites and neurovascular coupling. And then there's the endothelial mechanism, which changes vascular radius in response to shear stress and nitric oxide. So I'm, just for clarity, calling all of these mechanisms cerebrovascular regulation. And it is thought that the individual mechanisms are heterogeneous across patient demographics like sex and also things like diabetes status, where, for example, females are thought to have a more attenuated endothelial response. And it's also thought that these mechanisms might be heterogeneously impaired in brain injury. But for that reason, if we knew the functionality of individual mechanisms, it could be a key therapeutic target to potentially improve outcomes, but we don't know how to assess that mechanism, that functionality, or understand the dynamics of these mechanisms using neurocritical care data. And so just briefly, in this last project, we have developed a digital twin of the cerebrovascular system, where we took this general mathematized idea of how blood flow flows in bulk blood flow in the vasculature, and then we added mathematical equations for how each of these CVR mechanisms may function. And what we can do is we added 3 parameters called CVR functionality parameters that give us the presumed functionality of each of these mechanisms independently. I won't go into much detail, but we can use machine learning to estimate the function of each of these mechanisms using neurocritical care patient data. And what I show here is 6 patients for which we've done that. Cerebral sim is what we're calling this digital twin: cerebral blood regulation, latent state inference, and modeling. And what you see in red is the patient data. What you see in black is what we're calling the pressure passive model, or just a comparative model for which radius doesn't change, and then cerebral sim. And you can see for these kind of simple patients all the way up to these highly complex patients that cerebral sim seems to be able to forecast their blood flow. And I won't go into it, but we also get some estimates of how functional each of their vascular regulation mechanisms might be, which would be quite interesting. And then we can also use this personalized digital twin to forecast blood flow forward in time. And what you see here is, again, that pressure passive model, so the mathematical model where radius doesn't change, a continuously differentiable neural net, multivariate linear regression trained on the same data that cerebral sim is given, and then cerebral sim, and you can see that 5 minutes, 10 minutes, 30 minutes, and 60 minutes forward into the future, cerebral sim has a pretty strong capability or accuracy of being able to forecast cerebral blood flow. So I'm really excited about this project and I'm happy to talk more about it. We just released the preprint of this project. So I mentioned that I'm not a neurologist, but I have some pretty fantastic collaborators. So Soojin Park from Columbia and Brandon Foreman from the University of Cincinnati have just been an excellent collaboration in terms of sharing what actually matters in neurocritical care. And then my advisors, David Albers, Tellen Bennett, who's also a pediatric ICU doc, and Jake Stroh in our lab, who's done a lot of fantastic work in this area as well. So I'm happy to take questions. Feel free to shoot me an email or look at my website if you want to connect further. And I'll probably leave the screen up, but just go on to this. There we go, Q&A. Okay. Should I just read this question and start chatting?
Sure, if you want to, yeah, that would be great. I know we have some people in the audience whose names are associated with PRX, so I'm sure there will be some questions. Yeah.
Yeah. Okay. Great. So this is Farah. I hope I pronounced that right. This is fascinating work. Thank you. Since autoregulation is driven by low frequencies, would a low pass filter removing the high frequency heart rate help to remove this effect? Yeah, almost certainly. We wanted to make the algorithm as close to the standard PRX algorithm as possible in order to retain consistency across all of the fantastic work that's already been done. So that's why we did this approach, but I'm sure a low pass filter would also be a great approach.
Cool. Go ahead, Peter, you have a question or comment?
Hi. Yes. Wonderful talk, Jennifer. The main thing that I am happy about from this is you drawing again attention to the variability in PRX. This is something that we have been now trying to bring people attention to for some time. Now, what I, however, would like to point out very strongly is that there are many reasons why PRX is variable.
Yeah.
The fact that they are those, as you call, hyperparameters, and they were chosen for specific values. This was done based on the domain knowledge rather than just purely statistical, i.e., we knew, as you said in the beginning, about the time constant of autoregulation, and therefore any influence of the higher frequency, including the respiratory component, very important, which you don't mention in here, is detrimental. The reason the respiratory component, for example, is detrimental is that the waves that appear in blood pressure and ICP often directly transmitted independently to both from through the venous side, through the whole respiratory system, and that invalidates PRX itself. So there are many reasons why PRX is noisy. We should definitely look into ways of trying to unpick at least the periods where PRX may be more reliable. And so the fact that you calculated many PRXs, let's say, from different hyperparameters, the very short ones, they just are no-no because of the respiratory side, as I said. Yeah. But the other ones are just as valid. So there's not a big difference between 8 seconds, perhaps averaging 15 seconds, averaging 30 points, whatever. However, if the data reflects what our assumptions are about transmission of blood pressure to ICP, and only those waves in ICP that are transmitted from blood pressure we can pick up, then whether we take any of these hyperparameters, the longer ones, it should give us the same answer. If it doesn't, it means that there's something fundamentally not right with the assumptions. And so instead of trying to perhaps optimize one value of averaging over the other, perhaps we can use that approach to have an index of quality of PRX or validation of the assumptions. And that's just one thing that I wanted to mention. I'm sure guys on the calls you have some more. But what do you think about that, Jennifer?
Yeah, Peter, that makes a lot of sense. And I think exactly to your point, we typically found that the smaller averaging windows were much more problematic, as you say. Like this 5-second averaging window and the 6-second averaging window were far more problematic than these larger averaging windows. But no, I think that makes a lot of sense, especially since one of the challenges with this is that you all have done so much fantastic work in PRX in its current state that trying to completely change the algorithm might not be the best approach for the scientific community. So something like a quality flag makes a lot of sense. Or as you say, PRX is one of its things that makes it so beautiful is that it is really computationally simple to estimate. And so estimating many different PRXs within this optimal range and using that as a quality flag makes a lot of sense. I think that the respiratory comment that you bring up is interesting and important, and you're right, we did not reparameterize for respiratory, and that's primarily because the effects of respiration are just a little bit noisier compared to heart rate is quite easy to parse in the ABP. And we did find that was quite impactful. I think the only thing that doing something like a quality flag wouldn't address is the fact, this argument of when we have different amounts of heartbeats within an averaging window, you can get very biased, either biased towards the negative side or biased towards the positive side of ABP. And hopefully, if you take enough, which you do in PRX, that bias will smooth out, but it will still induce variability if you don't parameterize.
Can I ask one more question?
Yeah, absolutely.
Great. So actually, a question or comment and an observation. So with the heart rate influence and what you described here in very simple terms how this works, and there was a comment just before and a question about using the digital filters.
Yeah.
There are some of us, for example, in Uppsala, they use what we're doing with MINS is also a digital filter. It's just moving average with downsample. It's a very lousy filter. We all know that, the people that work within the signal processing, that this is really very shady filter. If you replace it with a proper Butterworth or elliptic filter, you do get improvement. And, we've done a little analysis like that years back, but it was not substantially higher statistically to warrant changing the standardization. So,
in what metric, do you mind me asking?
Excuse me?
Like it wasn't better in what metric?
So it improved statistical correlations to outcome and improved the variability a little bit. But this is the comment that I said at the beginning. The majority of problems of PRX perhaps are coming from this from the assumptions that are very often violated. Yeah. I mean, respiratory irregularity is one thing, but the other thing, this is the comment I wanted to make for the heart rate. If you look at the data of patients with arrhythmias, you can see how ICP is affected rapidly, instantaneously, with changes in blood pressure due to arrhythmic rapid changes. And these changes are too fast for the autoregulatory system to kick in. And therefore, they cause PRX to go to positive artificially. So there is this heart rate component there that is, I agree, very important, and for many reasons. Also possibly for the autonomic system, I think, yes, you hinted. But it's more complex and more multifactorial than just cropping the data in one way or another.
Yeah, certainly. I can't agree with you more. It's a complex system, and you're trying to use limited measurements to estimate something quite complex.
Absolutely.
And we have only addressed one of the many different things. So yeah, I can't agree with you more.
Exactly. So I'll stop talking. I am looking forward. I am looking forward to the other paper that you, because this is something that is very close to my heart, the physics informed machine learning. So I'm looking forward to reading your paper about that.
Thank you. Happy to chat more about it. I'm excited about it.
Excellent. Maybe at ICP meeting if you are going.
Yeah. We'll chat more offline.
All right.
Very cool. Well, if there are there no more questions in the chat, or if anybody else wants to has a longer question and wants to come off mute, we can do that as well. It's very cool. And it's very it's such your path to this, I think, is just so cool, Jennifer, that you coming from this other discipline and coming over into this world. It's just so fantastic, and you present it so well. It's really cool. And we're looking forward to trying to cajole you into presenting on that other topic as well.
Well, thank you for the invite, and thank you for how you all work well in trying to navigate the research while also the just the really great machines that you make. So yeah, I really appreciate this time and appreciate everyone for taking time out of your Fridays.
Cool. Thanks everyone for attending, and I know a lot of people will catch us on the replay, but we had some of our friends in the audience today that we see, and we thank you very much for spending your Friday afternoon, evening with us, because it's really cool work, and we were really excited to share. So thanks very much, and I guess with that we will close with one last thanks for Jennifer, and one more last congratulations. Let us know when the final date has come and you're official. I think that's amazing, and congratulations.
Thank you. I appreciate it.
Okay. Thanks very much.
Have a good day.
You too.